We are now ready to take a look at the binomial distribution, which is a specific type of probability distribution. Remember, we were starting to talk about probability distributions in the last section. And so a binomial distribution is a distribution that occurs when we have what's called a binomial experiment. And so we're going to run through what it means to be a binomial experiment, and then we'll take a look at some examples. So first of all, in a binomial experiment, you only have two possible outcomes. So in other words, either one thing happens or it doesn't happen. We're going to call those possible outcomes a success and a failure. So each time we run the experiment, we're going to complete a certain number of trials. And on each trial, we might have a success or we might have a failure. And so we're told here also, just for some notation, that the probability of success on any one trial is given by P, and the probability of failure on any one trial is Q. And because there are only two possible outcomes, P plus Q has to equal 1. So for example, like if we were looking at the probability that it was going to rain and raining was a success, then the probability of rain, if we were told that that was 20%, then a failure would be that it does not rain, right? Either it rains or it doesn't. And if the probability of rain was 20%, the probability that it doesn't rain has to be the other 80%, and 0.2 plus 0.8 would give us 1 or 100%. So that's kind of the idea. Another requirement of a binomial experiment is that there are a fixed number of trials, where n represents the number of trials, so basically the number of times you're performing the experiment, and each trial is a repetition of that experiment. And then finally here, the n trials are independent. So in other words, the outcome of one of the trials is not going to influence the next, and more specifically, it's not going to influence the probability of the next. So knowing the probability of the first is not going to affect the probability of the next trial. Also, we're repeating each trial using identical conditions. And since the n trials are independent, the probability of success P and the probability of failure Q need to remain the same for every repetition of the trial. So we're going to look at some notation, and then we'll get into an example. So the notation that we're going to use here, we're told that the outcomes of a binomial experiment have what's called a binomial probability distribution, and the random variable x represents the number of successes obtained in the n independent trials. And the way that we write this is x is distributed. So the squiggly line there means is distributed. The capital B stands for binomially, with n trials where the probability of success on each trial is given by P. So one other thing to remind you, or just to make you aware of, is that a success does not necessarily imply a good result. So for example, it just means that our event of interest occurred. So if we were studying probability of being diagnosed with cancer, then being diagnosed with cancer would be a success in that experiment. So I just don't want us to think that success always implies a good outcome. Some other formulas that we need: the mean of a binomially distributed variable is going to just be n times p, where n is the number of trials, and again, p was the probability of a success. And then the standard deviation is going to be the square root of n times p times q, where n is the number of trials, p is the probability of success, and q is the probability of failure. So we're going to look at an example here that talks about the case of coming into contact with someone who's carrying the flu virus. So we're told here that during a particular flu season, the probability of coming into contact with someone carrying the flu virus is about 0.04. Okay. So if x is our variable of interest, then our variable of interest here is coming into contact with someone carrying the flu virus. Okay. And specifically, X is going to represent the number of people who do that, right? It's going to be a count of the number of people who come into contact with someone carrying the flu virus. If we look back at what it meant to have a binomial distribution, first of all, there are only two possible outcomes. So either you come into contact with someone carrying the flu virus or you don't. So we do have the two possible outcomes. The next case is that there are a fixed number of trials. So as we get down here further, you'll see we look at a certain number of individuals. And then the last thing is that the N trials are independent. So that means that the probability of coming into contact with someone carrying the flu virus is about 0.04 for everyone, for all individuals, and that it doesn't change. So in this case, we would say that X does follow a binomial distribution where N is the number of trials. We haven't been told that yet. And P, the probability of success, so the probability that we actually have someone who comes into contact with someone carrying the flu virus, is 0.04. So what is a success? A success is coming into contact with someone carrying the flu virus. So again, success doesn't necessarily mean a good thing. The probability of success is P equals 0.04. That means that a failure would be not coming into contact with someone carrying the flu virus. And if the probability that we do is 0.04, then Q, which is the probability that we do not, is the other 0.96. Right? So in general, we could take 1 minus P to find Q. And the last one then here says, suppose you have a classroom of 28 people. So now what we've just been given is N, the number of times we repeat each trial. So we repeat the experiment 28 times. Okay. And what we're saying is we want to find the mean number of successes. So on average, how many people would end up coming into contact with someone carrying the flu virus out of a classroom of 28 people. So what we're told here is that we can find the mean by taking the number of individuals in the trial and multiplying that by the probability of success. So mu is N times P. Move that up a little bit. Where N is 28, P is 0.04. And so if we find 28 times 0.04, we get 1.12. And so we would say here that on average, out of a class of 28 people, 1.12 people would come in contact with someone carrying the flu virus. And again, that number, that average, depends on the probability of running into someone carrying the flu virus. So that changes depending on the severity of the flu and the time of year, and just the particular strain of the virus going around. Okay, so what we're going to look at next is an example of finding probabilities for certain observed values of x, so certain counts, numbers of successes in a binomial distribution. We're going to do that using our calculator, and we're going to stick with the same example we just had of the probability of coming into contact with someone carrying the flu virus. So the main thing I want to point our attention to here is that there are going to be 3 different cases that we look at in this example. And there's going to be a different process for each of those 3 cases. So we need to pay attention to what makes each case unique. So the first one here says, if we are going to try to find the probability that x is exactly equal to some specified value. So we have an exact count of the number of successes. And if that's the case, we're going to use that option in the calculator called binom PDF, which stands for binomial probability distribution function. And this is going to allow us to find the probability that x is one specific value. Okay. So if we want, for example, the probability that our number of successes is equal to 0, so that means that out of 28 people in the classroom, none of them come into contact with someone carrying the flu virus. The way that we're going to do that is we're going to go to second distribution. We're going to scroll down to option A here that says binom PDF. Make sure you're choosing the one that says PDF. Right underneath it is one that says CDF, and we're going to use that next. But when you want the probability that x is exactly equal to one value, you're using PDF. Trials, so this is asking us for n, right? So we did second distribution. We chose binom PDF. And then it's asking us for the number of trials, so that's n. And in this case, we looked at a classroom of 28 people. It's asking us for p, which is the probability of success. That was 0.04. And then it's asking us, well, what x value do you want me to find the probability for? We are looking for the probability that x is equal to 0, so that out of 28 people, if the probability of success is 0.04, we want the probability that we end up with 0 people coming into contact with someone carrying the flu virus. So we're going to hit enter, and we get 0.3189 if we round to 4 decimal places. And it asks us to interpret what that means in words. So we would say the probability is 0.3189 that in a class of 28 people, 0 of them run into someone carrying the flu virus. Okay, so we're going to do this one more time for a probability that x equals 5. So as a reminder, we went to second distribution, scrolled down to option A, which said binom PDF. Trials is still 28. P is still 0.04, but this time we want exactly 5 people to come into contact with someone carrying the flu virus. And we get 0.0039. And so again, that tells us that the probability is 0.0039, that in a class of 28 people, exactly 5 people run into someone carrying the flu virus. Okay, so just to make sure that we understand here what we're calculating, maybe I'll show you on the back side of this page for a second. Remember, X is our random variable. And what we're doing for each of these is we're calculating that probability of X. So just like we did with the example where we rolled 2 die and we looked at the possible sums and the probability of each one, now we're looking at X, where X, as a reminder, I guess from this page, X was the number of people who were coming into contact with someone carrying the flu virus. And so if I'm looking at a class of 28 people, the smallest number of people that could come into contact with someone carrying the flu virus is 0. And that could go all the way up, right, to all 28 people. All right, so those are the possible values. I would list them one by one all the way up to 28. And what we just found is that the probability that X is 0 is 0.3189. So we just found this guy, right? And then we also found the probability that X was 5, and that was 0.0039. Right, so I want to make sure you guys understand what we're finding. Basically, we're creating this probability distribution table. We could go through one by one and calculate each one of those, and we know the sum should end up being 1. And that's what we're doing when we're using binomial PDF, is finding the probability of one specific outcome. Okay. What we're going to do next is we're going to change gears a little bit, and this time we're going to be asked a question where instead of finding the probability that X is exactly equal to one value, now we want a range of values. So we're going to look at the probability that X is less than or equal to some specified value. And when it's X is less than or equal to, you're going to use the binomial CDF option instead of PDF. What this does is it always gives you the area under the cumulative distribution function that is to the left or below the value you enter. So that's why this works for less than or equal to. So if I want the probability that X is less than or equal to 5, that means either X is 0 or 1 or 2 or 3 or 4 or 5. So it's those 6 possible outcomes, 0 through 5. So the way that we do that is we're going to do second distribution, just like we did before. But this time, so let me try and write this down. This time we're going to scroll all the way down until we get to option B, which is binom CDF for cumulative distribution. So instead of just one value, we want a cumulative value. So binom CDF. And we're gonna hit enter. Trials, we still have 28. Our probability of success is still 0.04. And our X value, again, that we want X to be less than or equal to, in this case is 5. Oops. Our X value is 5. And then we're gonna go ahead and hit enter. And we get 0.9993 if we round to 4 decimal places. And so if we interpret this one's meaning, we're going to say the probability is 0.9993 that in a class of 28 people, five or fewer come into contact with someone carrying the flu virus. Okay, and so again, to make sure that we understand what we're looking at here, what we just did is we found the cumulative right there. We found the cumulative probability that X was 5 or less. So if we found each one of those probabilities and added them up, right? The probability that X is 0 plus the probability that X is 1 plus the probability that X is 2 plus the probability that X is 3 plus the probability that X is 4 plus the probability that X is 5, right? We add up all of those values. That ends up giving us the 0.9993, right? So we've almost got all of the probability just looking at 0 through 5, and that's because our probability of success was so small, right? The probability of coming into contact with someone with the flu was only 0.04. So it's not very likely that you're going to have very many out of a class of 28 that end up coming into contact with someone carrying the flu, and you can see that happening here. Okay, the last one that we're going to do, you'll notice that this time, instead of trying to find the probability that X is less than or equal to some specific value, this time we've switched it to greater than. And the reason this is a little more complex is because, as a reminder, this binomial CDF function always gives us the area to the left of the value we're interested in. And so we're going to have to use the complement rule, which was back from our chapter on probabilities, in order to answer this question. So if I want the probability that X is greater than or equal to 4, I think it's easier to see over here. If I want, and maybe I'm just going to redraw this real quickly. All right, so again, X can be anything from 0 to 28, 0 being no one runs into someone carrying the flu, 28 being all 28 students in the class run into someone carrying the flu. What we are asked to find in this last example is the probability that X is greater than or equal to 4. So what I'm looking for is the sum of all of those probabilities, right? The probability that X is 4 plus the probability that X is 5, all the way up to the probability that X is 28. Okay, so that's what I'm looking for. That I can't find directly by using the calculator. And the reason for that is just as a reminder, right? If I use binomial CDF and I plugged in X is 4, it's gonna give me the probability of 4 or smaller, right? 4 or below. And I don't want that. What we are going to use is the fact that we know that the sum of this probability distribution has to be 1, the sum of those probabilities. And so if I want this probability, I can find it by taking 1 and subtracting this probability. This is the probability that X is less than or equal to 3. So what you can see here is I can find the probability that X is greater than or equal to 4, right? Greater than or equal to 4 by taking 1 and subtracting the probability that X is less than or equal to 3. And so that's what we're going to need to do on this last part. And so I put a note there that we can find the probability that X is greater than or equal to 4 by finding 1 minus the probability that X is less than or equal to 3, but hopefully this helps you visualize why that works. So we're gonna go ahead and find this part, which is the probability that X is less than or equal to 3. That's gonna be binomial CDF with 28 trials. Probability of success 0.04, and X being 3. So let's go ahead and find that. By the way, if your calculator does not give you these outputs, trials P and X, you're just going to type it in comma separated on the main screen like I have written here. So we've got 28.04. We're going to change that to 3. And we get 0.9757 if I round to 4 decimal places, 0.9757. It's really tempting to just automatically circle whatever comes out of the calculator, but remember that was the probability that X was less than or equal to 3. That was this part right here, right? So what we just found is that this is 0.9757. So 97% of the probability is made up with just the outcomes 0, 1, 2, and 3. Okay, so these are just getting much more tiny and tinier and tinier as we go to larger and larger values of X. And so if we take 1 and subtract 0.9757, we'll get the probability that we're looking for, which is the probability that X is greater than or equal to 4. And so 1 minus 0.9757 is 0.0243. That's the answer we're looking for. And in terms of an interpretation here, we would say the probability is 0.0243. That in a class of 28 people, four or more would come into contact with someone carrying the flu virus.